Aluminum on the wires, copper in the walls. To understand the quiet pivot, start at the poles. Overhead transmission went aluminum decades ago, not because engineers fell out of love with copper, but because gravity never does. Aluminum carries about 61% of copper's conductivity at roughly a third of the weight. Stretch that across 1,000 towers and the math wins. You make the conductor fat, aluminum strands wrapped around a steel core, and you buy less sag, less cost, and a line crew that doesn't curse every reel. Meanwhile, inside buildings, copper stayed, not out of nostalgia, but because buildings are a different world. Tight spaces, thermal cycling, mixed metals, torque specs that live or die at a contractor's wrist. Copper's higher conductivity lets you pull slimmer gauge wire through conduits without turning every bend into a heat source. Its creep is low, terminations stay tight. In a breaker panel, those boring traits keep lights on. Here's where it gets complicated. Aluminum is not one metal in practice, it's a family of alloys with temper histories. Join it wrong and you get galvanic corrosion. Torque it wrong and you get cold flow, microscopic slippage under pressure that loosens the connection. Those weaknesses are manageable if everyone obeys the book. Oxide-inhibiting paste, proper lugs rated AL-CU, retorque schedules. But the book fights real life, rush jobs, mixed boxes on a site, one missing label on a lug. A single oversight becomes a hotspot. A hotspot becomes a failure under summer load. There was a moment in the 1960s and 1970s when aluminum tried to move into the walls in a big way. It ended with fires and lawsuits and a long memory baked into code. That legacy still shapes decisions. When copper prices jump, proposals reappear. Copper-clad aluminum for branch circuits, aluminum bus and panels, hybrid solutions that blend costs. Some of those are solid when properly engineered. Some are shortcuts that rely on everything going right forever. The stakes aren't abstract. In data center alleys, utilities lay new feeders at a pace that felt unthinkable a decade ago. The spec might read aluminum bus in the yard, copper in the building, bimetallic transition pads at the wall. That transition is a fragile piece, 2 metals, 2 expansion rates, 2 ways to fail if a bolt stretches or a surface oxidizes. Engineers sign off because they must. There isn't infinite copper and budgets aren't bottomless. But every interface adds an if. Across oceans, substitution shows up differently. Telecom didn't wait, fiber sprinted past copper on bandwidth and reach. That relieved one pressure, but it didn't free copper for everything else. The grid is still metal, motors are still wound. Even EV fast chargers, which live in a fibered world, feed on thick conductors and careful terminations. When automakers trim copper mass in motors, hairpin windings, tighter slot fills, they celebrate efficiency. They also tighten manufacturing tolerances and reduce repairability in the field. Meanwhile, procurement desks watch price spreads like weather. Treatment and refining charges fall, cathode tightens, cable quotes swell. A builder flips a spec, aluminum feeders instead of copper, same ampacity. On paper, it's clean upsized by code, approved lugs, correct compound. In practice, the installer's impact wrench becomes the hidden variable. On day 1, it holds. On day 700, under a heat dome, the joint breathes and a panel chirps. Now add geopolitics. Aluminum smelting follows cheap power, copper refining follows industrial clusters. Tariffs tweak those rivers. When one country raises the drawbridge, metal flows reroute overnight. A shipment meant for a Chinese rod mill is diverted to a US fabricator. A Latin American refinery slows on feedstock. A European plant idles on power costs. Designers downstream don't see the shipping manifest. They see a quote with a lead time and a price that forces a choice. Recycling could blunt the edge. Aluminum recycles with about 95% energy savings, copper with about 85%. But labor, quality control, and fragmented scrap streams play spoiler. High-grade copper scrap isn't always staying where it's generated. Some countries export the good stuff and import low-grade scrap back, with impurities that complicate refining. For aluminum, the alloy mix matters. The wrong scrap blend produces metal you can't confidently put in a connector rated for a hospital wing. There's a human layer people gloss over. Inspectors write up a panel and hand the contractor a punch list. The contractor knows the budget's gone and the client wants the ribbon cut Friday. The torque wrench comes out anyway, but a dozen other fires pull attention away. That's not negligence, that's reality meeting physics. Copper forgives more of those moments. Aluminum forgives fewer. So I keep saying aluminum on the wires, copper in the walls. Because that split captured a hard-won truce between cost, weight, and risk. It wasn't dogma, it was field wisdom. The quiet shift we're seeing doesn't rip that up, it frays it. A little more aluminum creeps inward. A little less copper shows up where it used to be assumed. The line between yard and wall blurs, one value-engineered change order at a time. None of this means aluminum is the villain. It means systems hate surprises. If we push substitution deeper, we have to upgrade everything around it. Lugs, training, inspection intervals, even the torque tools in a journeyman's bag. Otherwise, the failure doesn't announce itself at the lab bench. It announces itself at 3 a.m. with a burnt smell and a blinking alarm. Photons replace copper's data rent. While that was happening in the substations, something else was happening in the ground. The world's largest consumers of electrons, cloud regions, quietly evicted copper from the long haul. Photons took the lease. Not because copper was bad at carrying bits, but because fiber made speed and distance almost free. To understand why, we need to go back to the last mile that wasn't last. In the 1990s, telecom wrung miracles out of twisted pair, DSL pushing megabits through copper that had been nailed to poles for voice. Every extra megabit cost sweat, better modulation, more repeaters, more heat. Then a single strand of glass started doing kilometers at gigabits with a light at each end and almost no loss. It wasn't a fair fight. Copper charged rent for distance. Photons didn't. Data centers made the pivot ruthlessly practical. Inside the halls, short copper links still make sense for certain racks, cheap, simple, low latency over a few meters. But step outside the building and everything that matters is latency, bandwidth, and electromagnetic immunity. Fiber wins all three. Lightning can dance on a fence line and your signal doesn't care. You can run parallel strands the width of a hair and multiply capacity by lighting different colors through the same glass. DWDM turned a single route into a multi-track highway. What nobody knew at the time was how fast the appetite would grow. AI training clusters aren't just racks, they're neighborhoods of heat and hum, each node screaming for backhaul. Cloud regions stitch themselves together across states because no one campus can hold the load or the risk. Those stitches are glass. Lateral lines to peering points, glass. Long hauls across deserts, glass. Subsea cables stitched between continents, miles and miles of armored glass humming in darkness. There's a human story tucked in here. A field tech in Nevada told me their crew used to carry copper reels and splice kits. Now the truck has fusion splicers, OTDRs, and cases of clean wipes. The failures changed character. Instead of chasing water intrusion in a copper binder, they chase microbends, a crushed conduit, a dirty ferrule. It's still the same job, keep the bits moving, but the physics moved under their boots. This is where it gets counterintuitive. Fiber reduced copper's data rent, but it didn't relieve copper's power burden. Every glass path needs lasers, repeaters, transceivers, gear that drinks electrons. Every switch that pushes terabits throws off heat. So while photons carry the bits, copper still carries the amps. That means the more fiber we lay, the more copper we need in feeders and panels to feed the optics that made fiber essential. The pressure didn't vanish, it shifted lanes. And the geopolitics crept in again. You can draw the map of power in the data age by tracing fiber landings. Countries fight to host them, regulate who touches them, and mandate redundancy. When a subsea route snaps, markets feel it. When tariffs throttle the flow of optical transceivers, build-outs stall. Suppliers diversify sources of glass, performs, and lasers like miners diversify ore. It's the same game, concentration, choke points, alternatives, played with photons instead of cathodes. Meanwhile, builders learned a hard lesson. Fiber is cheap until the trench isn't. Permitting delays, right-of-way fights, rock you didn't expect, suddenly your perfect least-cost route turns into detours and blown timelines. That's when good enough shows up in proposals. Reuse an old conduit that wasn't designed for bend radius. Pull too many strands through a crowded vault. Accept a connector that should have been cleaned twice. The problems don't announce themselves day one. They appear 6 months into peak load, when a link flaps and a failover that never got rehearsed takes a hair too long. Then there's the substitution feedback loop. As fiber pushes deeper, copper manufacturers pivot toward power products, busways, switchgear, EV feeder cables. In a tight cathode market, capacity follows higher margin orders. That's rational. It also means the next time a hospital asks for high-spec copper data cabling, yes, some still do for specialized EMI environments, the lead time stretches. A metal that lost one domain gets more precious in the one it kept. The irony, fiber's dominance creates new reasons to be picky about the copper you keep. Clean grounds matter more when you're feeding sensitive optics. Transient suppression matters more when your entire operation depends on a glass thread that hates rough handling. The spec sheets for lowly power rooms start to look like lab notes. A missed bonding jumper can ring as loudly as a cut fiber. So did photons replace copper? For data rent, yes, brutally, decisively. For power, no, and the demand curve is still rising because every bright light on the end of a fiber needs electrons to glow. We traded one bottleneck for another and told ourselves it was progress. It is. It's also a reminder. When you solve the distance problem with glass, you make the amperage problem everyone's daily job. Motors and EVs, copper's last fortress. From their perspective, motors were supposed to be the safe zone. Engineers could shave copper from buildings and stretch aluminum on towers, but inside a traction motor there wasn't much to argue about. Copper wins torque density. It wins heat. It wins reliability when a vehicle spends a decade inhaling dust and rain and road salt. Now remember, the EV stack puts copper in 3 places that matter. The battery packs, bus bars, and interconnects, the inverters that chop DC into drivable AC, and the motor windings that turn electrons into motion. Each is a different negotiation with physics. In bus bars, you trade cross-section against temperature rise. In inverters, you fight switching losses and EMC. In windings, you chase slot fill, the percentage of a stator slot stuffed with copper rather than air and insulation. because every extra millimeter becomes torque. Here's where it gets crazy. Automakers are doing two things at once, switching motor topologies and compressing manufacturing tolerances. Hairpin windings, rectangular copper conductors bent into precise shapes, push slot fill past what round wire can achieve. That buys efficiency and shrinks copper mass per kilowatt, but it also makes the stator a precision object. A burr on a hairpin, a misaligned varnish cure, a tiny void near an end turn. Any of these become heat you can't afford when the highway is a 45-degree ribbon and the pack is at 20%. Permanent magnet synchronous motors change the game again. Magnets carry part of the field, so you can get the same power with less copper than an induction motor. Great in theory until Geopolitics walks in wearing a rare earth badge. If magnet prices jump or supply turns fragile, designs swing back toward copper-heavy induction topologies or hybrids that use fewer magnets. The fortress adapts, but the walls are still wrapped in copper. Meanwhile, a quiet copper diet is happening in the rest of the drivetrain. OEMs and Tier 1s trim mass and high-current cables with finer stranding and new insulation systems, push laminated busbars into tighter stacks, and polish every connector interface. That's rational. Copper is expensive and getting tighter. It also narrows margins for error. A connector that loved round wire might hate the stiffness of a hairpin busbar. A crimp spec that was fine at 400V might arc at 800V when a pin gets nicked. Field techs learn new failure signatures. A faint ozone smell after a fast charge, a flicker in the inverter that shows up only at one state of charge and one ambient temperature. And the chargers themselves. Fast DC stations are copper festivals. Massive feeders, fat DC cables, liquid-cooled leads to keep resistance manageable while you push 350 kW into a pack that's already warm. Designers are relentless about every milliohm. They also live with trade-offs that don't headline well. Make the cable thinner for customer ergonomics and you need more aggressive cooling. Use more aluminum in the upstream cabinet, and your lugs and transitions become a maintenance schedule. The bill of materials isn't a list, it's a map of vulnerabilities. What nobody knew at the time was how fast demand would compound. Add up vehicle wiring harnesses, motors, inverters, onboard chargers, home chargers, and grid upgrades to feed neighborhoods with multiple EVs. Then add the buses and delivery fleets that never sleep. Each EV uses multiples of the copper in a combustion car. Multiply that by millions, and copper stops being a component and becomes a gating factor. Price volatility doesn't just hit an OEM's quarterly. It shows up as design churn mid-program, as procurement pivots between grades and suppliers, as a software team rewriting charge curves to protect hardware that came in a hair different than the first prototypes. There's a worker at a Tier 1 plant in Ohio who still tells the story of a summer night when a small lot of hairpins arrived with a surface finish just out of spec. The varnish didn't wet perfectly. The motors passed end of line. The field return started 6 months later in Arizona. The fix was surgical new varnish chemistry, tighter supplier control, but the lesson stuck. When you squeeze copper mass, you squeeze the whole process. Every micrometer you remove comes back as discipline you have to add. Meanwhile, substitution nibbles at the edges. Aluminum in low-voltage harnesses in places that aren't mission-critical. Copper-clad aluminum in carefully controlled profiles. Even a few experimental rotor bars. Those aren't the heart of the fortress, they're the parapets. The keep is still copper windings, copper bars, copper buses, because when you ask for peak torque at a green light in August, the margins vanish. Upstream, the supply map tightens the screws. Mines take years, not quarters. Refining is concentrated. Scrap returns lag because the first big EV cohorts are still on the road. Recyclers prepare hairpin stators are disassembly puzzles, but the feedstock wave is years out. In the interim, OEMs hedge, lock multi-year cathode contracts, and quietly redesign for material efficiency that won't get a press release. So is copper's fortress unbreachable? For motors and EVs, it's the last place you'd bet against it. You can trade magnets for copper or copper for magnets, but you don't get away from metal that moves heat and current with minimal drama. The real risk isn't a single substitution. It's attrition, tighter tolerances, thinner cushions, more interfaces stacked across vehicles, chargers, and grids. The fortress stands. The moat is getting shallower. The coming supply gap. This is the moment everything changes. The demand curve stopped being a rumor and started showing up in orders. Grids are doubling backbones for AI load. EV factories plan millions of drivetrains. Utilities rush substation upgrades that used to sit on 5-year plans. On paper, copper supply is roughly 28 million tons a year. The near-term demand track plausibly heads north of 40 million within a decade. That isn't a price twitch, that's a structural gap. What nobody knew at the time was how hard it is to close that kind of distance. A mine is not a startup. From first drill to first ore can be 10, 15, even 20 years depending on permits, power, water, roads, and whether a community believes your promise will outlast your press release. Some projects in North America have taken decades. Meanwhile, ore grades are sliding, less copper per ton of rock, which means more energy and water per pound and more tailings to manage. The calendar is the enemy, so is geology. Refining even tighter. Mining is concentrated, refining is concentrated more. Chile dominates ore, China dominates the midstream. Smelters and refineries do not pop up in a quarter. They follow cheap, reliable power, stable policy, and environmental tolerance that's getting stricter everywhere. Treatment and refining charges that once fattened margins have thinned, at times even turning briefly negative, squeezing processors just when everyone wants more cathode. Add tariffs or export rules, and entire flows can reroute over a weekend. Recycling should be the pressure valve. Copper recycles well, secondary metal performs like primary with far less energy, around 85% energy savings versus primary. But collection and purity are bottlenecks. The copper you need is tied up in buildings, motors, and grids that live for decades. Above-ground stocks exist, but the urban mine doesn't empty on demand. Some countries export high-grade scrap and import lower-grade back, chasing short-term arbitrage while polluting the long-term feedstock. You can't run an EV program on wishful shredding schedules. Analysts began putting numbers to the feeling. Banks modeled deficits that don't close until the 2030s without unprecedented mine additions. Forecasts talk about millions of tons of extra demand, 7 to 9 million, arriving faster than credible supply. Traders see it in spreads between exchanges that whip unpredictably when policy moves yank cargoes from one route to another. OEMs feel it in lead times and in quiet supplier notes asking for flexibility on spec, because the last cathode shipment didn't match the first. Meanwhile, Africa's copper belt is waking up hungry. The DRC is now a top-tier producer. Zambia is pushing a revival with big capital and friendlier codes. New expansions at Kamoa-Kakula and fresh cash into old names like Mopani and Konkola. There's motion, and a lot of it from Chinese and Gulf capital. That helps, but it doesn't erase refining concentration or infrastructure limits. Rail, power, acids, ports, every constraint turns into a queue. And a new political mood runs through producer capitals. Keep more value at home. Exporting concentrates out and importing cathodes back looks less attractive to any finance minister with a deficit and a youth bulge. If you want the human version of supply gap, listen to procurement managers in OEMs and utilities. They used to treat copper like oxygen, always there, priced by weather. Now they sign multi-year offtakes, hedge volumes like airlines hedge fuel, and task engineers to cut kilograms without cutting performance. A car platform drops 10% copper mass in its motor windings. The inverter team pays the heat bill. A utility upsizes aluminum on a feeder. Operations inherits a new maintenance schedule for mixed metal joints. The savings are real. The complexity is realer. Price is the megaphone. When copper runs, EV wiring looms get redesigned mid-program, charge curves get rewritten to protect hotter connectors, and fast charger rollouts slip a quarter because the cabinet vendor couldn't get the bus bars they promised. Data centers postpone one campus and overbuild another where switchgear showed up. A hospital pushes a wing opening because the last test threw a thermal alarm on an AL-CU transition no one loved. Each delay looks small. Together, they're the shape of a constraint. There's a geopolitical layer nobody can ignore. Tariffs in one capital lead to stockpiles in another. Strategic reserves aren't just for oil anymore. Copper inventories become policy tools and panic buttons. Export restrictions on scrap in one block tighten refined markets in another. Sanctions shift trade to quieter ports. Smelters build friend-shored blends of concentrate to keep their ESG scores intact. The map is a living thing. So what fills the gap? All of it, and not fast. New African tonnage, Latin American brownfields, a few long-gestating projects finally crossing the line. Refining capacity where power is cheap and rules are clear. Recycling that moves from informal to industrial with traceability that banks accept. Design efficiency that trims copper per kilowatt without eroding reliability. And substitutions where they make sense, paired with the training and hardware that keep joints honest. Here's the part that matters for everyone not trading commodities. The gap won't look like empty shelves. It will look like schedules that keep slipping, quotes that require approvals 2 levels higher, specs that quietly change, and failures that cluster during heat waves and storms. It will look like 1,000 rational decisions made under pressure, adding up to a system with less slack than it used to have. Dr. Copper used to diagnose the economy. Now it's diagnosing the transition. The patient's heart is strong, the arteries are narrow. Where the ore lives and the choke points. To understand the strain, trace the map.